So what we're going to be doing today, guys, is kind of, you guys are actually going to do the demo that I did the other day. Okay, so you're going to use the air columns here, right? So these things right here, to calculate the speed of sound in here this morning. Okay, or some of you will be in the chem lab across the hall. Okay, just because when there's a bunch of tuning forks going, it's sometimes hard to tell which one is yours. On that note, everyone's going to use a different tuning fork. Okay, that way it's less confusing. You actually know what your tuning fork sounds like, and it's a little bit less disruptive when you hear a whole bunch of like really totally zen tuning forks humming away in the room. Okay, so everyone will use a different tuning fork. Everyone should still get the same number, because if we are, after all, in the same room with the same air temperature and all of that kind of stuff, and the wavelength of the, or frequency, sorry, of the tuning fork isn't going to make any difference to the speed of sound value. All right. So what we're doing is we're using closed pipe resonance to get the speed of sound. So you're going to do what I did the other day, fill this with water. So there's 4 large graduated cylinders in here. There's 4 large graduated cylinders in the chem lab. Okay, and the best way to fill this up is carefully. Okay, by lifting the PVC pipe that has the ruler on it up slightly so that it clears the bottom. Otherwise, if you pour into that, it just stays in the PVC tube, and none of the water gets into the clear part. Okay, so just lift it up a little bit. It's easiest to pour into that. Okay, or I've also had groups that just did this and poured into there, and then you just put this back in. You know, if you struggle with pouring, that's okay too. It's a bigger target, and I'm okay with that. I won't tell anybody. Okay, so totally up to you. So then what you'll do once you've got it filled, and you don't need to fill it like right. See, this is the problem with taking this part out. Okay, it's that whole Archimedes thing. Yeah. Okay, because I've had people they fill it and it's like to here, and they're like, all right, sweet, and they drop this in like that and splash everywhere. Okay, it's way So my suggestion is fill through the white tube. It's going to be way easier, and you only need to fill to about a few inches of the top. You don't need to go right to the top. Okay, you're going to be fine if you don't. Okay, so we're going to measure as many resonant points as we can for our tuning fork and air column. Okay, everybody should be able to get 2. Depending on your tuning fork, you might be able to get 3. I don't know that anyone's ever gotten 4. I suppose if you use the really, really short one, you might be able to get 4 resonant points. But if you get 3, you're good. Okay. The other day when I did this, remember I couldn't get the 3rd one. Or was it the 4th one? It was the 4th one I couldn't get. Okay. So you should be able to get 2 or 3 for sure. Okay. If you get a 4th one, great. If you don't, not a big deal. Okay. So you're going to measure those points. That'll be the first part. Once you have those points measured, okay, then we'll come back here and we'll talk about what we have to do with those numbers and have you guys work on the analysis just a little bit with your group. Okay, it's not something you're going to hand in, but it's a valid exercise for us to do. Okay, the day prior to our exam, where we definitely have a question about closed pipe resonance. On your test. Okay. All right, so we don't have to do a hypothesis or anything on this one. Our responding variable will be the length of the air column. Our manipulated variable will be the frequency of the tuning fork that we use. Okay? And then we'll be able to calculate a controlled variable. It's actually what we're calculating, and that's the speed of sound. It's the same for every single trial. Okay?
Just take out the hypothesis.
I don't want you to, I don't care if you write anything for the pre-lab part. Like I say, we're just doing this as a valid exercise. I'm not trying to make more work for you or anything like that. What I would say you should probably write down would be the stuff to do with the analysis when we walk through that. Kind of just like some extra problem solving or explanation kind of stuff of the concept of air columns. Okay. All right. So every group is going to need 1 air column, 1 graduated cylinder. If you're going across to the chem lab, there's 4 graduated cylinders in there, so you don't need to take one of these ones. Okay, take one of these and 1 set of tuning forks. Right, now for the tuning forks, okay, they are usually tied together here with the strap. Okay, just unroll it, and in there, some of them have a hammer. Well, it's actually not a hammer, it's a mallet, which is, it's called a mallet technically. Okay, and then it's got a set of tuning forks. You can choose whichever tuning fork you want to use, but try not to pick anything close to the groups that are near you, because it gets confusing. Okay, now my suggestion is actually not to use the mallet. Okay, I find that people chip the tuning forks with the mallet because they miss. And I know that seems ridiculous, but it's so true. Okay, because people are like, all right, and then just at the last minute, like you can see this one's full of nicks. Okay, and then like at the last minute they miss and they hit it with the handle, or they hit it with the hard plastic part instead of the rubber part, and it eventually kind of changes the frequency of sound that the tuning fork makes. So my suggestion is to use the strike pad instead. I find people miss this less often because you're swinging the tuning fork and not this. So you just set this on the table, and as in any activity requiring hand-eye coordination, keep your eye on the target, because I've had people miss this too, but they miss it less. Okay, and all you have to do is strike it. Okay, and it'll vibrate pretty good. You're gonna have to strike this thing a lot. Okay, if this thing starts to go down, hit it again. Okay, just keep it so that it's vibrating as much as possible when you're doing the lifting of the tube, so you get the best possible sound, and of course you're listening for the loud areas. When you find one of those loud areas, don't just go, oh, it's right about there. Strike it again, move it up and down past that spot until you are sure you're at the loudest point, kind of like what I did the other day, right? It wasn't a, oh, there it is, loud, and I stopped. Okay, I kind of went up and down, I struck it again, and then kind of found that spot. Okay, you'll have to do that as well, okay, but it's a pretty straightforward thing to do. When you're done, just make sure the tuning fork gets back in, the strike pad gets back in. For the mallet, if yours actually does have a mallet in the kit, just bring the mallet back, because I'm actually trying to take them out of each tuning fork kit. Okay, so when you're done with the tuning forks, okay, don't double knot this, just give it one overhand knot, and you're good. Okay, so once you've got your 3 resonant points recorded, come back and we'll talk about the analysis. You and your group can sit down and do the analysis part. That's all we'll do, no conclusion, no evaluation, anything like that. And then you'll get a little bit more time to do some wave review stuff today. Okay? All right. Have at it. All right, so let's have a look at the analysis part of this now, guys. Okay, so hopefully everybody got at least 2 points. Okay, if you got 3, wonderful. Okay, but let's just kind of look at what we're going to be doing here. So we have our frequency. We know what the frequency of our tuning fork was. Okay, we have the length of our column of air in meters. Okay, if we got 3, great. Right. So now what we want to look at is for question number 1. Okay, and maybe just kind of write this out on a sheet of paper or something. Okay, how far is each of the first 3 resonant points from the reflecting surface? So basically, you don't have, you're filling in this chart. Okay, this is the length of the column, so that's basically that. Okay, calculate. Oh, sorry. In terms of wavelength, sorry, not in terms of meters. Okay, so in terms of wavelength, maybe just draw. I know a few of you did it already. Okay, just draw. What did the waveform look like for the first point? What did the waveform look like for the second point? What did the waveform look like for the third point? Right. So our first one is the 1/4 thing. Okay, calculate the wavelength of the sound from the tuning fork for each resonant point and show your work. Okay, so your first resonant point was 1/4 of the wavelength. What was your second? Calculate the wavelength. What was your third length? Calculate the wavelength. So do it 3 times. Should you get around the same number? Hopefully. Okay, hopefully you're going to get around the same number. Right? Then, using that number, calculate the speed of sound for each one. So you're going to do that 3 times. Hopefully, again, that number is going to be pretty close to the same number each time. Okay. When you calculate the wavelength for each of the resonant points, do the answers agree? So basically, just go through, write down some answers for the 5 analysis questions, and then we'll talk about them in a few minutes when you're done. Okay. So if you can perform those calculations. So number 1, kind of diagrams. Okay, number 2, actually calculate the wavelengths for each one of those, calculate the speed of sound for each one of those, talk about 4 and 5, okay, get an answer written down for 4 and 5, and then we'll talk about them as a class. Okay? Okay, so for our first question, in terms of wavelength, how far is each of the first 3 resonant points from the reflecting surface? Well, the first one is 1/4 of a wavelength. The next one is 3/4 of a wavelength from the reflecting surface, and if you got a third one, it's 5/4 of a wavelength from the reflecting surface. Okay. For question number 2, if we're going to calculate the wavelength of the sound from the tuning fork, okay, we would say, all right, for the first one, okay, L equals 1/4 times lambda, or lambda equals 4L. Okay, and we can calculate the wavelength by simply dividing by 0.25 or multiplying by 4, whichever for that first one. Okay, for the second one, the length equals 3/4 times lambda. So divide both sides by 3/4, you've got lambda. Okay, and the same thing for the last one. Length equals 5/4 times lambda. Divide both sides by 5/4 and you've got your wavelength. And you should get pretty close to the same number for each one of those. Okay, did that hold true for everybody? All right, then all you have to do is calculate the speed of sound for each one. Well, you got V equals F times lambda. You know what the frequency was because it's stamped on the tuning fork, okay, and you calculated your wavelengths for each one of these, right? So you can calculate the speed of sound. What are we getting for some numbers here?
334 meters per second.
334, okay. 333. I take it wasn't close to that number. What'd you get?
189.
Oh, I feel like something went really wrong there.
Probably.
Okay, I'll have a look at that calculation. What did the other group get? Because I've only got 2 here. We had more than that.
We had 3 different ones.
Okay,
The highest was 352.8.
okay, and the lowest?
It was 339.73.
Okay, I mean, that range is well within where we should have been, yeah. Okay, so around probably like 340, somewhere in there. Okay, I'm missing another group. I think, yeah, I got the group already. David told me. Carol, what did you guys get?
We did it wrong.
Oh,
Oh, yeah, it's.
I'm trying to
okay.
figure
Okay, I mean, in the ideal world, I mean, it's about 20 degrees in here, and we're at altitude, so we should be getting somewhere kind of in the high 330s, okay? Maybe even the low 340s would be a fairly reasonable answer. The other day when I did this, okay, I got, I think, 341 with you guys, and I got 343 with my afternoon class. Now, that could be accounted for by the fact that it got warmer in here through the day as well, and the change in temperature could have altered the change, or could have caused that increase in speed. The temperature got higher, so the speed of sound got higher as well. Okay, I'd like to think I was actually that consistent, but it was probably just reading it a little differently each time. Okay, but that should be about what we get. Now, when you calculate the wavelength for the resonant points, do the answers agree? And they probably were fairly close. Okay, certainly within a centimeter or 2, and that's pretty reasonable. Okay, because you're judging something, right? There's that kind of human judgment error where you're going, was it louder there or was it louder here? And it's making a difference of between 1/4 and 1/2 of a centimeter maybe. Okay, so it's fine if they weren't exactly the same because you did have to make a bit of a judgment call on where was it actually the loudest. Okay, and why do you want to start with the shortest one and increase rather than look for the longest one?
because it's just easier.
Yeah. You get an idea of where the next one should be if you start with the shortest one, and so you don't have to just waste your time slowly lifting the thing out to find the second one. You're like, okay, my first one was 33, my next one should be in the 90s somewhere. All right, perfect, I know where to start looking. Okay, you don't have to bother with the 60 centimeters in between. Okay. All right, is that making sense, everybody? Okay, so we got kind of a chance to work with that, see it in action a little bit. Okay, are there any more questions about the waves exam? tomorrow that I can help you with? Okay, because I have a couple more of the sample questions that we didn't get to yesterday, okay, that I'll put up that we can kind of work our way through. Just, you know, it's valuable to do them because we didn't get a chance to finish them yesterday. Did we do this one?
No, we didn't.
Okay, so we got to this, no, we didn't do this. Did we do the submarine one? Okay. We did this one though.
Yeah.
Okay, all right, try the submarine. Okay, so what we know on this one is we know the wavelength, okay? We know it's 1.2 meters, okay? It takes sound waves 4.5 seconds to return to the sub. So how long did they take to reach the bottom? 2.25 seconds. Okay, and they're traveling at 1,500 meters per second. What frequency is being used? Okay, so I actually don't need the time. I don't know what I was doing with that question. I think the second part of that was supposed to be what's the depth of the water? Yeah, but I messed it up. Okay, so we've got the wavelength and we've got V if we're looking for F. Okay, F equals V over lambda. Okay, and we have our 1,500 divided by 1.2 meters. What does that come out to?
1,200
1,200 and
something.
something?
1250.
1,250. Okay, we have two significant digits, so 1.3 times 10 to the 3 hertz. Okay, would be the frequency of that sound. All right. Could you figure out the depth of the water? Yeah, okay, that would be this trick here with dividing the time in half, okay, and we would simply have a D equals V times T question. 1,500 times 2.25 would give us the overall depth of the water. Okay. It's very,
Decimal.
oh, 2.25, yeah. That's better. It's still very deep. All right, so 3.4 times 10 to the 3 meters deep. Okay. All right, everybody all right with that one?
Why is it a different answer? Like, why is the frequency different when you do the 1 over 2.25?
Because that doesn't calculate frequency. This is not period, this is time.
Oh,
Yeah, does that make sense? Okay, all right, give this one a try. What kind of problem asks us for acceleration? Hooke's law. Yeah. Okay, so for this one here, okay, if we're looking for the acceleration of a mass on a spring and we know the spring constant is 3.5 newtons per meter, okay, and we know the mass of the mass, 0.85 kilograms, okay, and we know that it's 0.38 meters from equilibrium, okay, we know that because it's oscillating, that its net force is provided by the restoring force. Okay, so we can simply say that the restoring force is equal to F net, which means K times X equals M times A. All right, since they didn't tell us whether that 0.38 is right or left or whatever from equilibrium, we can't really give a vector on our acceleration other than possibly towards equilibrium. That would be the best that we could do. Okay, so I don't need to put in the negative here because it won't matter. So I'm going to have that I'm looking for acceleration, so I'm just going to divide both sides by mass, and then I will have 3.5 times 0.85, no, sorry, times 0.38 divided by 0.85. All right, so we should have an acceleration of 1.6 meters per second squared toward equilibrium. Okay, questions on that one?
If the spring constant did say it goes to the right or to the left, then would the acceleration be the opposite of that?
Well, the spring constant is never gonna be right or left, but if the
Yeah.
displacement was right or left, then yes, the acceleration would be opposite. That, and I would leave the negative in that case. Uh-oh. That's weird. Oh, and now it goes. Okay, that's it. That's all the questions I made up the other day. So, you got a little bit of time left. Do you want to go through the review package that I gave you? And if any questions come up on that, we can certainly talk